Hello, and welcome to the Dizzy Doctor, a cozy little corner where curiosity settles in gently and science takes the slow, scenic path toward slumber. Tonight, our soft-spoken voyage leads us into one of the most mysterious companions of our lives, a force we live by, rely on, feel slipping through our fingers, yet rarely understand. Time. It flows invisibly. It shapes every moment. And sometimes, it teases us, especially when we're waiting for a kettle to boil. Isn't it funny how that last minute stretches into an age? But before we begin unraveling this quiet, ticking mystery, I'd love to know, where in the world are you listening from? And what time is it for you, right now? Fitting, isn't it? A story about time. And yet, here we are, all of us in different time zones, scattered across the globe, arriving together in this exact moment, in our own unique slice of the clock. If this voyage brings you comfort, sparks your wonder, or gently winds down your day, I'd be so grateful if you clicked the like button, maybe even subscribed. It helps this calm little space reach others who might be searching for a peaceful pause. Now, I do hope tonight's journey doesn't awaken your mind to much, but if it keeps you up, just a little, well, at least you'll come away with a few new thoughts about the universe's hidden rhythm. So settle in, let your thoughts slow, and let's begin. Because somewhere between ticking seconds and timeless centuries, between sleepy dreams and morning light, lies the story of time. Time has a strange personality, doesn't it? 10 minutes spent in traffic can feel like an hour, while 10 minutes with a favorite hobby disappears faster than the last biscuit in the tin. And yet, clocks tick steadily, second after second, minute after minute. So, what's really going on? The answer begins not in physics, but in the mind. Our perception of time, our inner sense of when things begin and end, is far more flexible than we imagine. Psychologists call it subjective time, and it's deeply shaped by things like attention, emotion, and memory. In other words, how time feels is often very different from how it's actually passing. Let's begin with a feeling we all know: waiting. Imagine yourself in a quiet waiting room. The walls are beige, the magazines are ancient, and somewhere, a clock ticks loudly, like it's trying to win a prize for most irritating sound. 5 minutes here can feel like an eternity. That's because your brain is under stimulation. When very little is happening, your attention turns inward, and that inward focus heightens your awareness of every tick, every talk. Now contrast that with a lively conversation, or losing yourself in a good book. In those moments, your mind relaxes its grip on time. It says, "We're busy now. No need to keep track." And suddenly, hours have vanished without a trace. This mental state has a name. It's called flow, coined by psychologist Mihaly Csikszentmihalyi. It's when you become so deeply absorbed in the present, your sense of time quietly fades into the background. Interestingly, newness plays a role too. When you experience something unfamiliar, your brain needs more effort to process and record it. Later, when you reflect on that moment, it feels as if more time passed, because your mind laid down more mental footage. That's why summers from childhood feel endless. Your brain was constantly logging fresh, vivid memories. As we grow older and routines settle in, our minds compress those memories. Fewer highlights, shorter mental reels. Time feels like it's speeding up. Emotions color time as well. Fear and anxiety slow our sense of time. Joy and excitement speed it up. Some researchers believe that in moments of danger, your brain records more details per second, creating the illusion of time stretching out. This has been described by people in accidents or emergencies, a slow motion effect. Not because time changed, but because the memory is richer. And then there's boredom, time's most famous distortion. We often say, time flies when you're having fun. But the reverse is just as true. Time crawls when you're bored. Neuroscientists have found that when you're bored, the brain's internal pacemaker, yes, that's a real thing, becomes more active. It creates more pulses in your perception, making time seem to drag, like an overenthusiastic drummer, tapping every dull second of your day. Time doesn't just live in clocks or calendars, it lives in language, in culture, and deep within the ticking of our biology. In English, we speak of time like it's money. We spend it, save it, waste it, or run out of it. But not every culture sees it this way. Some indigenous languages, like Hopi, for example, don't describe time as a line you travel along. Instead, they treat time as something shaped more like a landscape, a field of experience, not a track or tunnel. In some parts of the world, people even point behind them to indicate the future, because it's unknown, and point ahead to show the past, because it's already seen. Quite the opposite of how we imagine things, yet equally beautiful. But what about our inner clocks? Surely, we must have some biological sense of time, some quiet tick inside us, telling us how long something takes. And yes, we do sort of. Humans operate on a built-in rhythm known as the circadian rhythm, a 24-hour internal cycle that regulates our sleep, temperature, and hormone levels. But this is more of a daily timer than a stopwatch. For shorter durations, seconds or minutes, scientists believe we rely on a mental timekeeper, a kind of internal stopwatch, working behind the scenes. It's not located in just one part of the brain, but rather spread across a network of regions, including the basal ganglia and cerebellum. These areas seem to produce a steady stream of neural pulses, and when we estimate how long something has lasted, we're subconsciously counting those pulses. But, as you've likely guessed, we're not always great at it. Our sense of time can be wildly inaccurate, especially when we're distracted, overwhelmed, or emotionally stirred. There's even something known as the return trip effect, the peculiar feeling that the trip home always feels shorter than the trip out, even when both take exactly the same amount of time. Why? Well, on the way there, your brain is busy, taking in new information. On the way back, it already knows the route, and so, time feels like it slips by faster. And who could forget the most universally mysterious distortion of time, the snooze button? Somehow, those 9 minutes between alarms feel shorter than any other 9 minutes in the universe. While there's no official scientific explanation yet, it's likely due to disrupted sleep, fuzzy consciousness, and that tired old internal stopwatch throwing up its hands and saying, "I give up." So, what is time? As we experience it's not just the ticking of a clock, or the shadow of a sundial. It's a feeling, a perception, a trick of memory and attention. It flows with your mood, shifts with your age, and dances through the languages we speak. It hurries when we're in love, lingers when we're afraid, and sometimes vanishes altogether. And while physics may one day fully explain what time is on the grandest of cosmic scales, the time we feel will always remain something deeply, exquisitely human, wobbly, wonderful, and at times, delightfully unreliable. If time is a mystery, then our attempts to measure it are a testament to both human ingenuity and a certain impatience. From ancient sundials to atomic clocks, we've spent millennia trying to tame this invisible river, to shape it into something we can see, count, and ideally schedule around. Because as much as time refuses to wait for anyone, we humans are awfully fond of asking it to hold on. Just a minute. Let's step back, far back, into the deep past. Long before calendars or clocks, time was told by the sky. Our ancestors, with nothing more than careful eyes and deep patience, became quiet observers of the heavens. The rising and setting sun, the swelling moon, the turning seasons, these natural cycles became the world's first calendars. No batteries needed. The ancient Egyptians were among the first to formalize timekeeping. Around 1500 BCE, they built towering obelisks, giant sundials, that tracked shadows as the day moved forward. These obelisks helped divide daylight into parts, though those parts changed with the seasons. An hour in summer might be longer than an hour in winter, but it was good enough for farming, for prayers, for the rhythms of a growing society, probably still running late for something. Next came water clocks, simple, elegant tools used by Egyptians, Greeks, and Chinese alike. These devices measured time by the steady flow of water from one container to another. They worked at night, an upgrade from sundials, and some even chimed bells or moved figurines as the hours passed. You could say they were the original smart devices, just a bit wetter. Across the world in Mesoamerica, the Maya developed astoundingly accurate calendar systems, tracking both lunar and solar cycles with cosmic precision. Their long-count calendar could measure spans of time lasting thousands of years, a feat of celestial knowledge from a people without metal tools or beasts of burden. Their grasp of time was breathtaking. Meanwhile, back in medieval Europe, mechanical clocks were beginning their slow, echoing entry into history. At first, they were enormous, clunky, loud devices installed in churches and monasteries. They didn't have faces or hands. They rang bells instead, marking the passing hours mostly to remind monks when it was time to pray. In a way, The monks were the world's first alarm clock users, though likely more serene about it than we are at 6 a.m. A big breakthrough came in the 14th century with something called the verge escapement, a clever bit of engineering that allowed for a more regular, controlled release of energy. This meant clocks could finally get smaller and more reliable. Eventually, dials and hands were added, so time could be seen, not just heard, tolling from a tower. From there, the pace of invention began to tick faster. By the 17th century, a new invention swung into the spotlight, quite literally. The pendulum clock, introduced by Dutch scientist Christian Huygens, changed everything. Pendulum clocks were accurate to within a minute a day, a staggering leap forward compared to earlier models, which could drift off by hours. If time were a wild horse, the pendulum was the saddle, letting us ride it with newfound control. Suddenly, minutes had weight, schedules could tighten, and the rhythm of daily life began to beat more precisely. The need for even greater accuracy rose with the age of exploration. Sailors navigating vast oceans needed to know not just where they were, but when they were. Determining longitude required knowing the exact time at a fixed location, like Greenwich, no matter where you were in the world. Enter John Harrison, an English carpenter with an astonishing mind and a heart full of determination. He spent decades perfecting marine chronometers, ultra-stable clocks built to withstand the tossing and turning of ships at sea. His fourth model, the H4, revolutionized navigation and earned him a place in history, though not without a few eye rolls from seafarers who'd grown used to reading stars and trusting gut instinct. By the 20th century, we entered a new age, the age of quartz. Quartz crystal oscillators, first developed in the 1920s, were a revelation. When exposed to an electric current, quartz vibrates at a beautifully consistent frequency. These vibrations became a new kind of heartbeat, more accurate, more reliable than anything mechanical. Suddenly, clocks and watches could be cheap, portable, and precise enough to keep trains running on time, or at least leave us with no excuse when they didn't. But even quartz has its limits. If you want to know the most accurate time on Earth, you'll need to look smaller, much smaller. You'll need to go atomic. Developed in the 1950s, atomic clocks measure time using the natural vibration of atoms, usually cesium or rubidium. A single cesium atom, for example, oscillates 9,192,631,770 times per second. That number isn't just trivia. It's the official definition of a second. These clocks are so precise that if you let one run for 100 million years, it would be off by less than a second, which is helpful if you're very, very patient or very serious about punctuality. Today, atomic clocks are used to synchronize everything from GPS satellites to internet servers, global banking systems, and even the ticking of your smartphone. Without them, your maps wouldn't work. Your bank transfers could fail. Half the planet might miss their Zoom calls. Time, once measured by sunlight and dripping water, now dances to the tiny vibrations of invisible atoms, ticking quietly in the world's most secure laboratories. And yet, despite all this precision, time still feels personal. We can divide it into hours, minutes, and seconds. We can watch it scroll across glowing screens, but no matter how fine we slice it, we each live it differently. Why did we start measuring time at all? Some say it was to guide prayers, others to know when to plant and harvest, to track the seasons, to schedule trade. But perhaps it's because humans, for all our stargazing and storytelling, are comforted by rhythm. The steady beat of time, however invisible, gives our days shape, a kind of quiet order in a world full of chaos, a whisper from the universe that says, "You are here, now." For most of history, time was deeply local. It rose with the sun, it slept with the stars, it moved gently guided by bird calls, bell towers, and the occasional enthusiastic rooster. Then came Isaac Newton, a man who didn't just describe the world, but wanted to pin it down. That included time. Newton, the 17th century English physicist with a famously wild hair and an Apple-related anecdote or two, gave us a model of the universe that would hold sway for more than 2 centuries. In Newton's eyes, space and time were the stage, a grand, invisible framework upon which the universe's drama unfolded. The actors, planets, apples, cannonballs, even bicycles, could move, fall, or spin. But the stage itself never moved. Time in this model was absolute. It ticked forward at the same rate, everywhere, for everyone, forever. In Newton's own words, absolute, true, and mathematical time, of itself, and from its own nature, flows equably, without relation to anything external, like a river, steady and fair, flowing onward whether anyone is counting or not. This vision made sense. Drop a stone today or tomorrow, here or in a far-off town, Newton's equations could predict its path. Time, as he saw it, was reliable. Constant is absolute. Time became the foundation of classical mechanics, the physics of motion, force, and gravity. And for centuries, it worked beautifully. From swinging pendulums to the orbits of planets, Newton's framework was a powerful tool. Time, in this world, was universal. But there were doubters. Philosopher Gottfried Wilhelm Leibniz, Newton's intellectual rival and co-creator of calculus, disagreed. To Leibniz, time wasn't a thing in itself. It wasn't an independent river, flowing on its own. Time, he believed, was relational, a way to describe change. Without events, he argued, time had no meaning. Picture a clock ticking in a completely empty universe. For Newton, it's still measuring time. For Leibniz, it's just a very quiet paperweight. This debate between time as real or relational would echo through centuries, and for a long while, Newton's model ruled. It let engineers build machines. It let sailors chart courses. It gave scientists the comfort of predictability. But eventually, the seams began to show. In the late 1800s, cracks appeared in Newton's grand stage. Physicists studying light and electricity noticed odd things. Experiments showed that the speed of light remained the same, no matter how fast you were moving. That didn't fit Newton's world. In Newton's model, motion and time were absolute. If a car sped up, it should catch up to light a little faster, shouldn't it? But it didn't. Light always raced ahead at the same speed. This puzzle simmered, until a young man, working in a Swiss patent office, decided to rewrite the rules. His name was Albert Einstein, and in 1905, at the age of just 26, he introduced the world to something extraordinary: special relativity. One of Einstein's key ideas was that the laws of physics, including the speed of light, are the same for all observers, no matter how fast they're moving. But if light always travels at the same speed, then time can't. This leads us to one of the strangest consequences in all of science: time dilation. Simply put, the faster you move, the slower time passes for you compared to someone standing still. If you boarded a spaceship and flew off at near light speed, your onboard clock would tick more slowly than one back on Earth. You'd age more slowly. Your tea would stay warm longer. You'd miss entire seasons of your favorite shows. It sounds like science fiction, but it's been tested and proven. In one famous experiment, scientists flew atomic clocks around the world on commercial airplanes. When they compared them to clocks left on the ground, the airborne ones had ticked slightly slower, only by a tiny bit, but enough to prove that speed really does bend time. And then there's the twin paradox. Imagine two identical twins. One stays home. The other boards a high-speed spaceship, zooms through the galaxy, then returns. When they reunite, the traveling twin is younger, not because of better sunscreen, but because time actually passed more slowly for them. It's not a contradiction. It's a feature of reality. But speed isn't the only thing that will time. In 1915, Einstein went further. He introduced general relativity, a sweeping theory of gravity that changed everything. In this model, gravity isn't a force pulling objects together. It's the curving of space-time itself. Picture a soft, stretchy mattress. Place a bowling ball in the center. That's a massive object, like Earth or the Sun. Now imagine smaller objects rolling nearby. They're pulled inward, not by a force, but because the space beneath them is curved. And if time were painted onto that mattress, it would stretch and bend too. This means time runs slower near massive objects. Stand near a black hole or your friend's suitcase, and time ticks more slowly for you than for someone farther away. Again, this isn't just theory, it's been measured. In one experiment, two ultra-precise atomic clocks were placed at different altitudes, one at the base of a mountain, the other at the top. The lower clock, closer to Earth's center of gravity, ticked just a little bit slower. Even a height difference of just a few centimeters can cause time to shift. Technically, your head is aging faster than your feet. This quiet stretching of time, this gentle, gravitational warping, might seem like distant science. but it's happening all around you. Right now, above your head, a constellation of GPS satellites orbits the Earth. Those satellites move fast. They're also farther from the planet's gravity, so their clocks tick both slower and faster, depending on the effect. If those two effects weren't constantly corrected, if the system didn't account for Einstein's relativity, your phone's location could drift off by several kilometers every single minute. Without those corrections, your GPS would lead you into a lake or a stranger's garden. Time doesn't just pass, it wobbles, and our technology, it has to wobble with it. So, what does this all mean? Einstein showed us something profound, that time isn't absolute. It's not a universal, steady river, flowing through a quiet landscape. Time is part of the fabric of the universe, a soft thread, woven together with space. It bends, it stretches, and it flows differently depending on speed and gravity. That means your time, the rhythm at which you experience life, depends on where you are and how you move. It's strange. It's beautiful. Time is no longer the same for everyone, everywhere. It's personal, a little like your taste in tea. Einstein's work didn't just change the math in textbooks, it changed how we think about reality itself. Time isn't a fixed backdrop. It's part of the dance, shifting with the rhythm of matter and motion. Even if you don't feel time stretching or shrinking in your day-to-day life, it's happening. Every moment you live is being gently sculpted by motion, gravity, and perspective. So next time someone says, "I'm running out of time," you can smile softly and say, "Actually, time is running out differently for you, depending on your velocity and your distance from Earth's core." Then pause, sip your tea, and maybe duck. Let's imagine something strange. You wake up one morning, and everything is running backward. Your toast leaps out of your mouth and lands, perfectly buttered, on a plate. Your tea grows hotter with each sip. Raindrops rise, silently, back into the clouds. It's peculiar, it's dreamlike, and yet, not entirely forbidden by the laws of physics. You see, in most of the fundamental equations, Newton's, motion, quantum mechanics, time doesn't have a preferred direction. They work just as well backward as they do forward. If you filmed two particles colliding and played it in reverse, the math would be fine. The universe wouldn't complain. And yet, in real life, time always feels like a one-way street. Eggs break, but they don't unbreak. Ashes don't reassemble into books. We remember the past, but not the future. So why does time seem to flow in only one direction? This leads us to a powerful concept, soft in name, but mighty in meaning: the arrow of time. It's a metaphor, a way to describe the direction in which time flows, and its foundation lies in one of the universe's messiest rules, the second law of thermodynamics. It says this: in a closed system, entropy, or disorder, always increases. In simpler words, the universe has a tendency to move from tidy to messy. You can scramble an egg, but not unscramble it. Your socks will vanish one at a time, never return as matched pairs. A glass that shatters on the floor becomes a memory. The reverse is statistically possible, but wildly improbable. This drift toward more disorder gives time its direction. It's why we remember moments in a line from before to after. It's why the past feels solid, and the future feels wide open. Entropy isn't about what's impossible, it's about what's unbelievably unlikely. The deeper mystery: if entropy must always increase, then why did the universe begin in such a low entropy state? Why was the cosmic draw so neatly organized at the very start? After all, if we begin with mess, where does the arrow point? Most cosmologists believe that, just after the Big Bang, the universe was incredibly smooth, uniform, and ordered. As gravity took hold, things began to clump, collide, ignite, and entropy rose. But why it started neat, why the arrow points from simplicity to complexity, remains one of physics' most poetic open questions. Some wonder if entropy, time, and the shape of space itself are deeply linked. Others think we may be asking the wrong question, like a fish trying to understand water. The arrow of time isn't just written in entropy. It appears everywhere, in the way we remember, in how we act, in the structure of the cosmos itself. Let's begin with the most personal of all: memory. You remember the past, not the future. That's not just storytelling, it's biology. Memories require physical processes, traces left in your brain, connections carved by neurons, signals stored and replayed. And all of that happens in the direction entropy flows, from order to disorder. We don't remember the future, because it hasn't happened yet. No traces exist. There's also the causal arrow, the logic of cause and effect. You flip a switch, and the light turns on. You don't see the light flicker, then decide to flip the switch. This sequence, this reliable march from cause to consequence, is deeply entangled with entropy. When you flip that switch, you add energy to the system. Light spreads, heat dissipates, and the universe becomes a little bit messier. Then there's the cosmological arrow, the flow of time written in the stars themselves. We now know that the universe is expanding. Galaxies are drifting apart. Space is stretching. Everything is cooling down, slowly, quietly, patiently. This expansion gives a direction to the cosmos, a kind of universal tick that moves forward. Now imagine, just for a moment, if the universe were contracting, would time feel like it was running backward? It's a playful idea, one that physicists enjoy exploring. But for now, the important thing is this. All of these arrows, entropy, memory, causality, expansion, point the same way. They align, they whisper together, and that's strangely comforting. It suggests that time isn't just a trick of perception, but something woven into the very structure of reality. A path, carved by heat and history, by motion and memory. Still, not everyone agrees that time, as we live it, is fundamental. Some physicists believe that the arrow of time is an emergent property, something that only arises when complex systems like us observe simpler systems like tea cooling, or stars aging, or snow melting. In some interpretations of quantum mechanics, time isn't even a thing, not a force, not a flow, just a label, a coordinate for how different states relate to one another. The universe doesn't feel time. We do, and that's the curious thing. No matter how deeply we study entropy, or memory, or math, time remains a kind of illusion we believe in, something we ride like a current, yet can never quite step outside of. We don't know what's ahead, we can't go back, and yet, we live by its rhythm, minute by minute, memory by memory. Maybe, that's the real arrow of time. Not in the stars, but in us. If classical physics treats time like a train schedule, steady, reliable, always on track, then quantum mechanics plays jazz. It improvises, it dances, it asks questions with no fixed answers, and sometimes tosses in a cat in a box, both alive and not, just to make things interesting. Welcome to the quantum world, where reality grows fuzzy, and time becomes a suggestion. In the classical universe, you can say, that object is there, doing this, right now. But in the quantum realm, particles don't have precise positions. They exist as probability clouds, shimmering waves of might be and maybe not. And time in quantum mechanics plays a surprisingly minor role. It shows up not as a hero, but as a background character. In equations like the Schrödinger equation, time simply keeps things moving. It tells the wave function how to evolve. But unlike in relativity, time in quantum mechanics doesn't bend. It doesn't warp or twist. It's just there like a silent metronome, keeping tempo, never asking questions. This creates a curious divide. Quantum mechanics describes how things change over time, but it doesn't really explain what time is. In fact, it treats time the way Newton did, as something fixed, external, absolute. But space, energy, matter, they're jittering, tangled, unpredictable. Try to combine this with Einstein's view, where space and time are flexible, fluid, part of the same cosmic cloth, and things get messy. This is known as the problem of time in quantum gravity. When scientists try to describe the entire universe using quantum mechanics, they run into something strange. Time disappears. One of the key equations, the Wheeler-DeWitt equation, looks a lot like Schrödinger's, but there's no time variable. Just now, no past, no future. Just a kind of eternal stillness. So what's going on? Is time even real? Or is it an illusion, something that emerges only when we step back and watch? Some physicists believe that time is emergent, not fundamental, like temperature or waves in water. A single molecule doesn't have a temperature, but trillions together, then temperature becomes useful. Maybe time is like that too, a concept that only makes sense when you zoom out far enough. Others look to entanglement, the mysterious quantum connection where two particles, no matter how far apart, can instantly affect one another. Some theories suggest that time's direction, or even time itself, may arise from the growth of entanglement, the spreading web of quantum connections. And then there's the many worlds interpretation. In this view, every quantum event causes the universe to branch. Flip a coin, the universe splits. In one world, it lands heads. In another, tails. Every decision, every measurement, creates a new thread. Time, here, isn't a river. It's a vast tree, endlessly branching, with you at the tip of just one shimmering leaf. And somewhere out there, another you who made a different choice, and forgot their umbrella this morning. Time isn't just measured by stars, equations, or ticking clocks. It hums softly within you, in your cells, your sleep, your hunger, your heartbeat. Whether you're a night owl, an early bird, or something more like a perpetually groggy pigeon, your body runs on a clock, and it's a very old one. This internal rhythm, or rather, a whole network of them, is what scientists call your circadian rhythm. From Latin, circa diem, it means about a day. These rhythms are biological cycles that follow a roughly 24-hour loop. They influence everything from when you feel sleepy, to how your body processes sugar, to your mood on a rainy afternoon. And they are found across nearly all living things: humans, animals, plants, even some bacteria. If it's alive and vaguely organized, it probably keeps time. At the center of it all, tucked deep inside your brain, is a small region with a long name, the suprachiasmatic nucleus, or SCN, if you're feeling cozy. It's part of your hypothalamus, sitting just above where your optic nerves cross. A strategic position because it lets your inner clock sync with sunlight. When your eyes catch the morning light, the SAN gets the signal. It begins sending out instructions, adjusting hormones, body temperature, and more. It's like your brain saying, the sun's up, let's get moving. Gently. One of its key jobs is controlling the release of melatonin, sleep hormone. As the day fades, melatonin rises. Your body softens. You begin to slow. By morning, melatonin drops, and you're nudged back into waking, or at least, that's the idea. Whether or not you listen is another story entirely. Now here's something curious. Your circadian rhythm isn't exactly 24 hours. Most humans naturally drift a little long, about 2 hours, give or take. If left alone, no clocks, no phones, no sunlight, we'd slowly fall out of sync with the Earth's rotation. That's where morning light comes in. It resets the clock, it anchors us, keeps our inner rhythm tuned to the world outside. But if that light disappears, or shifts suddenly, things get weird. Enter jet lag. Jet lag is what happens when your inner clock is out of sync with the environment around you. Fly across several time zones in a few hours, and your body thinks it's midnight when it's lunchtime. Your brain adjusts quickly, but your digestive system, your immune system, they're still unpacking from last week. Modern life adds other complications. Long ago, humans woke with the sun and slept with the stars. Today, we've invited a neon owl into our living rooms. Glowing screens, bright bulbs, endless blue light. This confuses our brains. Blue light suppresses melatonin, delays sleep, and nudges our internal rhythm later than nature intended. It's not that we're night owls. We're just surrounded by daylight imposters all holding remotes. And not everyone's clock ticks the same. Some people are natural morning larks, springing out of bed with suspicious joy. Others are night owls, hitting their stride as the world winds down. These traits, called chronotypes, are partly genetic. So if mornings feel like an existential crisis, it's not just willpower. Your biology might genuinely disagree with 6 a.m. alarms. And who are we to argue with evolution? Circadian rhythms influence more than just sleep. They touch body temperature too. Your core temperature drops in the early morning, making waking up feel like shaking off. A soft frost then rises gradually through the day. It peaks in the late afternoon, which is why athletes, musicians, and performers often do their best work later in the day. Their bodies are warmer, more alert, tuned for precision. It's also why early morning presentations can feel like trying to solve puzzles inside a refrigerator. But biological time reaches even deeper. It shapes how your body processes food, fights illness, and heals. There's an entire field devoted to this, called chronopharmacology. It studies how a drug's effectiveness changes depending on when you take it. Turns out, timing matters. The same medicine might work better in the morning or the evening, depending on what it targets and when your body is most receptive. Even cancer treatments, blood pressure medication, and vaccines are beginning to be timed with the body's internal rhythm in mind. The future of medicine may well be synchronized. But it's not just humans. Plants live by time, too. They open their leaves to morning sun, close them gently at night. Some even begin to stir before the light arrives, anticipating dawn. This isn't just a passive response. It's an active internal rhythm, one that continues even in constant darkness. A sunflower doesn't follow the sun because it sees it. It turns because it remembers. Animals, too, from birds to bees to mice, move by hidden clocks. Circadian rhythms guide migration, foraging, hibernation, even song. And then there are the fungi, quiet forest dwellers living in the shade of trees. They, too, keep time, releasing spores, growing and resting in rhythmic patterns that hum beneath the soil. All of this paints a picture, a living earth, beating not to mechanical clocks, but to an ancient, biological rhythm, a pulse older than words. Not the time of ticking watches, but a living time marked by light and dark, warmth and cool, hunger and rest. A soft drumbeat shared across species, so the next time you feel that afternoon slump or find yourself unusually alert after sunset, it's not random, it's rhythm, your cells, remembering the sun, following an invisible beat, the same beat that guided our ancestors across forests and deserts, that opened flowers at dawn, that lulled creatures to sleep beneath the stars. And even now, beneath the hum of electric lights, beneath alarms and calendars, that quiet rhythm still plays, softly, faithfully, always. Have you ever noticed how time seems to play favorites? A holiday week floats by like a feather in a breeze, but the last 10 minutes of a Zoom call you didn't want to be on, that feels like you're trapped in a slow-cooked rice pudding of eternity. This isn't just poetic exaggeration. This is psychological time, the wonderfully warped way your mind perceives the passage of moments. And it often has very little to do with clocks. If physics asks, what is time? Then psychology asks, how does time feel? And the answers are beautifully inconsistent. Let's begin with a familiar phrase. Time flies when you're having fun. Oddly enough, it's true. When you're deeply engaged, laughing with friends, lost in a project, watching something captivating, you stop noticing time. Your attention is elsewhere. You're fully present. And because your brain isn't keeping score, time seems to vanish. On the flip side, boredom stretches time like taffy. When nothing holds your attention, a slow meeting, a silent cue, a very detailed explanation of crypto, your brain starts watching the clock. And time, like a watched pot, refuses to boil. There's also a twist between living and remembering. Time. When you're in the moment, time might feel fast or slow depending on your mood and focus. But when you look back on it, the effect can reverse. Imagine a week spent hiking unfamiliar terrain. Each day flew by while you were there, but when you look back, it feels long, packed with vivid detail. That's because novel experiences lay down more memories, more bookmarks. And your brain, when flipping through them later, thinks, wow, that must have taken a long time. Contrast that with a week of identical routines. Wake, work, watch, sleep. That week might have felt slow as you lived it, but in hindsight, it blurs. Fewer highlights, fewer memories, less time. Psychologically, this might explain why time seems to speed up as we age. As children, everything is new. Your brain logs each first in rich detail. First snowfall, first bike ride, first heartbreak. As adults, we settle into patterns. Fewer surprises, fewer vivid memories. Our brains switch to compression mode, and decades start to fly. But it's not just novelty. Emotion shapes time, too. In moments of fear or anxiety, time seems to slow. This isn't just storytelling, it's been measured. People who experience sudden shocks, like bungee jumps or simulated falls, often report that time stretched out. One theory says that your brain, under stress, records more details per second. So later, when you recall it, the memory feels denser and longer. But interestingly, in the moment, time doesn't actually slow. In lab tests, people don't perform better during the event. They just remember it as longer afterward. So when your mind says, that was the longest roller coaster drop of my life, your stopwatch says, actually, it was 2 seconds. Still impressive, just not Matrix level. At the heart of all these perceptions lies one quiet force: attention. Where your mind goes, time follows. When you pay close attention to time, like waiting for cookies to bake, you feel every tick. But when you become absorbed in music, in art, in conversation, time recedes into the shadows. This is the magic of mindfulness, of flow, of simply being present. Practices like meditation invite you to focus on a single breath, a single sound, a single sensation. And when you do, something soft happens. Time begins to dissolve. It's not that you're in a trance or unaware. It's that you've stopped measuring. You're not chasing the next hour. You're living inside this one, and for many, that feels like freedom. On the more mysterious end of the spectrum are altered states of consciousness, deep meditation, emotional intensity, even certain substances. In these states, people report time stretching, collapsing, even disappearing entirely. Some describe a sense of timelessness, not a distortion of time, but the absence of it, as if they stepped outside the river and watched it from the shore. Neurologically, these experiences may be linked to changes in the brain's default mode network, a system involved in memory, identity, and time processing. When this network quiets, our usual sense of self and time can gently dissolve, and what remains? Stillness, presence, a strange kind of clarity. Children, too, have their own relationship with time. For very young kids, time is fluid and often irrelevant. Ask a 5-year-old how long 5 minutes is, and they might say forever, or until I finish this cookie. Only as they grow and are introduced to clocks, schedules, and that dreaded phrase, just a few more minutes, do they begin to align with adult time. Some might say, that's the true loss of innocence. And then there's anticipation, the brain's built-in time machine. When we're looking forward to something, time seems to drag, and when we're dreading something, the same. That's because we start imagining, rehearsing conversations, picturing outcomes, mentally, stepping into the future, and all that mental time travel uses the same neural machinery we use to recall the past. Time, in this way, becomes elastic, stretched by hope, compressed by worry, bent softly by our thoughts. So, is psychological time reliable? Not at all. Is it logical? Rarely. But is it deeply human? Absolutely. We may live in a universe of ticking atoms and swirling galaxies, but the time we experience, the time that paints our days, is made from memory, emotion, focus, and dreams. It's time felt, not measured. And maybe that's why it feels so strange, so personal, so beautifully, heartbreakingly inconsistent. No journey through time is quite complete until we ask, can we travel through it? It's a question that's launched 1,000 science fiction tales, inspired curious thought experiments, and ignited more than a few debates at midnight dinner parties. The answer? Well, maybe, but it's complicated. Time travel, at least, in theory, isn't strictly forbidden by physics. In fact, Einstein's general relativity tells us that space-time, that flexible fabric of the universe, can bend, twist, even loop under the right conditions. And if space-time can form loops, then time, too, might fold back on itself. Let's start with the easier direction, traveling into the future. This one, it's real, and it's already been done. Remember time dilation. If you travel close, to the speed of light, time slows down for you, relative to someone who stays still. So, if you zoomed around the galaxy at near light speed, you'd return to Earth having aged less than those who stayed behind. You'd arrive in the future. No flux capacitor required. This effect has been tested. Astronauts aboard the International Space Station, zipping around the Earth at high speed, age just a little more slowly than people on the ground. It's tiny, but measurable. Future time travel. Done. Now comes the real mind-bender. Traveling into the past. Here, things get twisty. General relativity does allow certain solutions that permit backward travel in time, in theory. One idea involves closed time-like curves, loops in space-time where an object could return to an earlier point in its own history. Imagine walking a lap around the universe and arriving back at yesterday. Another idea involves wormholes, hypothetical tunnels connecting 2 points in space-time. If you could stabilize a wormhole and accelerate one end near light speed, then bring it back, the two ends would experience time differently. Step through, and you could emerge in the past at least. That's the math. The problems, they're monumental. First, We don't even know if one exist. Second, if they do, they might collapse instantly. Third, keeping one open would require something known as negative energy, a form of energy more exotic than anything you'll find in a kitchen drawer. Still. Let's imagine for a moment. Suppose we managed it. Suppose we actually built a time machine and took a step into the past. Then what? Well, we encounter a classic paradox. The most famous is called the grandfather paradox. It asks, what if you were to travel back, and whether by accident or by strange circumstance, prevent your grandfather from ever meeting your grandmother? That would mean ... you'd never be born. But if you're never born, then how could you have traveled back at all? It's a logical puzzle, a cosmic contradiction. So how do we make sense of this? Can the past be changed, or is it somehow ... protected? Physicists and philosophers have proposed a few possibilities. One is the block universe model, the idea that all points in time, past, present and future, already exist. Time doesn't flow. It's fixed like pages in a book. Not moving through time, you already exist on every page. In that view, even if you did travel to the past, you wouldn't change anything, because everything you do was always part of what happened. You were meant to be there, a thread, already woven into the story. Another idea comes from quantum physics, the many worlds interpretation. It says that every choice or action causes the universe to branch. So if you went back and changed something, you wouldn't affect your original timeline. You'd simply create a new one, a different reality, unfolding on its own. In your world, nothing would change. But in the new one, anything could happen. And then there's something called the Navikov self-consistency principle, which suggests that time prevents paradoxes, that no matter how hard you try to disrupt the past, events will always align in a way that preserves consistency. You might drop the note, the call might not go through, something would shift, and history would stay intact. It's as if the universe has its own quiet safeguard, no contradictions allowed. Of course, these are still theories. No working time machine exists. No traveler has stepped from a glowing portal to greet us, though the internet loves a good mystery photo. And here's a curious thought. If time travel to the past becomes possible one day, then where are all the visitors? Shouldn't we see people from the future snapping photos with dinosaurs, wandering through Renaissance fairs, in very convincing costumes? Some suggest that travel might only reach back as far as the moment the first machine is activated. Others imagine that time travelers would blend in, unnoticed. Or maybe, just maybe, traveling back in time is impossible. No matter how fascinating, the equations appear. And perhaps that's a good thing. As much as we dream of returning to relive memories, correct mistakes, or make different choices, maybe the one-way journey of time is part of what makes it precious. We move forward, moment by moment, unedited, imperfect, wonderfully human. And maybe that's enough.